Hi everybody, welcome back to the lecture Multimediale Werkzeuge, this time about Wavelets and JPEG 2000. So last time we saw the artifacts coming from applying the DCT, for instance, in JPEG. We got those blocking artifacts from the 8x8 blocks. And here's an example where you can see those artifacts again. So I can zoom in so that you can see those artifacts better. So here you can see on the left is the original, and on the right you have 66 times compressed with JPEG, compressed and decompressed. And here you can see, when you look here in the background, you can see those blocking artifacts. So in original it's a little bit grainy, right? But here in the decoded, the graininess is gone, but instead you have those artificial block boundaries here in the background and also here at the edges. So this is the typical JPEG artifacts. Now JPEG 2000 is another standard which uses not the DCT, but instead so-called wavelets, of which we will learn more today. And they basically produce different artifacts, as you can see here. So you can compare it. Here is DCT and here is wavelets coming from JPEG 2000, also compressed 66 times. And you can see those artifacts, they look different. So it's less blockiness but more blurry. So the graininess here is also gone in the reconstructed, because the graininess is a very fine pattern. A fine pattern which is visible to the eye but doesn't really contain any useful information. So it's gone. It's basically a victim of the high compression, this graininess. So it's not really a big loss, but it's basically replaced by those artifacts. So now the artifacts are appearing more blurry, and you could argue that this looks more natural than those artificial edges that appear in the background here. Right here, those artificial edges which are not really there. Here it's more blurry, so it's somewhat more natural looking. So overall the quality is maybe similar, but the artifacts they look now more natural, and maybe they are less conspicuous if you don't have the original as comparison. Right? If you just look at the decompressed, then it's maybe less conspicuous, less obvious than JPEG. Right, so here the entire picture. So all in all, probably more natural. So let me zoom out again. Yeah, so observation, the artifacts look different. JPEG 2000 has less blocking artifacts, but some fuzziness. So the cause here would be that JPEG 2000 has a different subband decomposition. So what does the subband decomposition of JPEG 2000 of these wavelets look like? So in principle we have a 2-band decomposition instead of 8 subbands, which is cascaded. So we have a low pass and a high pass for each stage, so for the low and high spatial frequencies. So here you can see this basic building block. You have your input signal, the image, one dimension, for instance horizontally. Then you split it into a low pass signal and a high pass signal. Half-half. This is the lower half and this is the upper half. And since we have only half the bandwidth, we can downsample it by a factor of 2 according to Nyquist. Right, assuming that we have perfect filters here, which of course is never true, but we assume it anyway. So this is in principle analog to the DCT, where we have 8 subbands and downsampling by 8. Yeah, okay. So now we have 2, right? So very similar. But now instead of having just one, we have several of those, right? We have this arrangement in a tree structure. So this can be seen here. So again, here on the left, we have our image First one-dimensional, for instance, the rows, we subdivided in upper half, lower half. But now we continue with the lower half. So the lower half is again split into two. So again, lower half. So this will be lower quarter, lowest quarter, and this would be 1/4 above. And then here again, this lowest quarter is again split in two. So this would be the lowest eighth, and then the next eighth. But observe that we don't split the higher frequencies of each branch. They stay, right? And this has the advantage that for the highest frequencies, we only have this downsampling by a factor of 2, and that means we get more spatial samples, right? We have less downsampling, and that means we have more positional precision for higher frequencies, and this is particularly important for edges in an image. So if you have an image which has high frequencies mostly around edges, then this becomes important because we want to keep the edges precise at their position. We don't want to spread edges out because that would make them look blurry, right? So this avoids blurriness, and this is also one of the causes of the blocking artifacts when you have the DCT. Even the high frequencies have the downsampling factor by 8, and basically those edges will be spread out and they become then blocky. So this is something that avoids this blockiness by using this tree structure, because you have a higher spatial resolution for high frequencies which appear around edges. On the other hand, if you have graininess, like in this example picture, then this doesn't really help because the graininess appears all over the place. And then also the wavelets don't help, as we just saw in this example. So this helps for edges, right? Not for graininess or, say, a picture of grass where you have the same problem as with the graininess. Yeah, so basically this assumes that you have mostly smooth images with only a few edges around the boundaries of objects. Yeah, so now we can apply the same for horizontally and vertically. So let me write it out. Horizontally, vertically. So now we cascade horizontal and vertical filters, which you can see here, which we would need in an image. Basically, we do the same as for the DCT. Remember, for the DCT, we applied them first on the rows horizontally and then on the columns vertically, and we do the same here, right? Here we have high pass, low pass horizontally, right? This division into 2 subbands instead of 8, and then we take the result and apply vertical filtering and downsampling to it, right? So at this point here, we have 4 subbands, 2 horizontally and 2 vertically, and this basically looks like a small 2x2 DCT, right? If we had a 2x2 DCT, it would give us the same appearance, except that the filters for the corresponding filters of the DCT are much smaller than of wavelets. This is actually one of the biggest differences. Wavelets have much longer filters than the corresponding filters of the DCT filter bank. So here, this would be, for instance, the upper left corner of our frequency domain. Yeah, so then we take the lowest frequencies here. So this is the upper left, which corresponds to DC, right at this point. And then it's subdivided again into 4 small quadrants. So again, this would look like a 2x2 DCT applied to the DC coefficients coming out of this stage. So again, we would have 4 smaller quadrants, right? And this way, the upper left-hand corner would have a finer and finer resolution in the frequency domain, right? So this is basically this cascade concept. So in this way we have a non-uniform frequency resolution due to this structure. We get the highest frequency resolution at the lowest frequencies, which means the lowest bandwidth of the filters. At the same time, we have wider filters at high spatial frequencies, but a significantly higher spatial resolution than with the DCT. That means, for example, that edges are less blurred because their spatial frequencies remain in their place. This can be illustrated as block processing with blocks of size 2 at high frequencies, or like the 2x2 DCT. A 2x2 DCT. No. So this is a block of size 2x2 pixels. So we have a high frequency resolution at low frequencies, so that's good for compression. And we have high spatial resolution at high frequencies, and this is good for maintaining edges. So maybe that's what I can add here. Good for compression and high spatial frequencies, good for keeping edges sharp. Okay, so in principle this cascading can be continued indefinitely. The deeper band is further split. In practice, however, only a few steps or iterations of this tree structure are used. The following picture shows the impulse response of the two filters in this cascade. So now we can see actually that those filters are much longer than what we would use in a DCT. Remember, here we have a two-band decomposition, but in the DCT that would mean that we only have filters of length 2, right? Remember, in the DCT the length of the filter was always identical to the number of subbands. So if the number of subbands is 2, the length of the filter is also 2. And with just 2 samples in the impulse response of our filters, we basically get very bad filters. So that's why in wavelets we use much longer filters, which means the impulse responses is covering several of those blocks. That means we have overlapping blocks basically as the effect. Yeah, so here are the filters. We still have limited attenuation in the stop band. We get approximately only minus 15 dB, except if you look at this high pass of JPEG 2000. And here is the frequency response. So maybe I should rewrite this as high attenuation only in the stop band, only for the high pass, around DC. So here's the high pass, and you can see it has the length of 7 samples. Yeah, so 7 instead of just 2. And here is the resulting frequency response. So this is for the analysis. And synthesis would be different. So here you can see dashed red line is the passband, the ideal passband. So in the passband it looks really good, right? So almost perfect. And then the stop band, so-so. So here, close by the passband, this looks like a very broad transition band. And then here you get very good attenuation at frequencies below, say, 0.1 normalized frequency, where 1 would be Nyquist, right? 1 is the Nyquist frequency here, and here would be 1/10 Nyquist, and below you get an attenuation exceeding minus 50 dB. So this is actually pretty good. And this is one of the characteristics of these wavelets, that they have very good attenuation near DC for the higher band. And this is important because in images, usually most energy is located close to DC. right, and natural images. And we don't want to have those DC energies spill over into the high band, because that would reduce our compression performance. We want to keep the DC in the low band, not into the high band. And this is what we can achieve here with this filter. Yeah, and here you can see the representation in the spatial frequency domain. So this is the structure of the subband decomposition. Remember, for the DCT we have a checkerboard of 8x8 fields, right? 8x8 coefficients. Here it's unequal, right? You can see here we have the horizontal and vertical frequencies, and these are the corresponding subband images. Remember, for DCT we had 8x8 subband images. The upper left hand corner was the DC image with the edges of 1/8 of the original. And here we have the subband images which have unequal, non-uniform size. You can see here the high frequencies have a size which has edges of 1/2 of the original. Here, these are the subband images analog to the subband images of the DCT, but here they have just half the size horizontally and vertically. And when we go towards lower frequencies, here in the upper left hand corner, this would be DC. So DC is small, surrounded by 3 of the same size, but then when you go to higher frequencies, they increase in size, which means they have a higher spatial resolution, right? And this was important for keeping the edges in place. And that's why the highest frequencies here have also the highest size, which means we have more pixels to represent precise locations of the edges. Yeah, so the size of the subband images is very different depending on the spatial frequency. And this is the characteristic of a wavelet decomposition. And here you can see an example for a test image. So here's the original. So this is actually a popular test image for images. Here this is called Cameraman, and this is an early digital image. And you can see this is actually the campus of the Massachusetts Institute of Technology. Here you can see the library, here the meteorology building, and here the radar on top of it. And this is the sports field, and here you can see a cameraman. And this is also nice because you have sharp edges here, right? So here at the legs of the camera you have crisp edges. Also around here the cameraman, and you have grass. So this is high frequency content which is not localized. Here in the edges you have localized high frequencies. Then you have you have uniform areas here in the sky, so good for testing. So then on the right you can see the resulting wavelet decomposition. Right, so here you can see the result. Maybe you can zoom in a little bit to see it better. So, okay, out a little bit. Okay, so here on the upper left hand corner you can see the DC image, the DC subband. And you can also see we just have 2 stages, right? Because here this was coming from the first stage, the high frequencies, and then the lower frequency was subdivided again by 2 by 2. So this is just 2 stages of the subband decomposition. And here you can see the resulting DC, which has 1/4 of the length of the sides. So smaller image of the original. And then here you can see neighboring the edges. So here the vertical edges, right, to the right, and here the horizontal edges. So here you can see the edges coming from the horizon here. So here horizontal edges, and here you have diagonal edges. So here, like the legs of the camera, for instance, you can see. And when you go to the right and to the bottom, you can see the more sharper edges. So again here, the vertically or close to vertical edges. Here the horizontal or close to horizontal edges, and here the diagonal edges. And you can see, since we have a relatively high resolution image here for the high frequencies, we keep the edges in place. Right? They have a high spatial resolution in this way. For the grass, it's not really working. You can see the grass is basically appearing everywhere. So for the grass, we don't really get an advantage because we have to encode the grass in any of those images. Right? There's no compaction for the grass. So for the grassy areas, we could as well use the DCT. It wouldn't make any big difference, except for the artifacts, the blocking artifacts. The wavelet artifacts would still look more natural. Yeah, so I think this basically shows nicely the principle of the wavelet decomposition as opposed to the DCT composition. Remember, for the DCT we had the Ilmenau test image, and there we had a uniform sized subband images. Yeah, so then there are also problems with wavelets. That's why they are not used universally. The frequency resolution at high frequencies is too low for some applications, like speech and audio. Right? For images, we have that most energy is concentrated near DC. This is not true for speech and audio. Right? And then also we have problems with aliasing. Aliasing occurs when we don't have ideal filters. Right? Remember, we have this low pass, high pass, and we saw that this high pass is far from perfect. It's pretty good near DC, but then it has a very wide transition band, and that means we get aliasing because we violate a Nyquist, because we do the downsampling by 2 anyway. So the finite attenuation of the subband filters results in alias components because of the violations of the Nyquist condition, which propagate through the cascade of the tree structure and must finally be coded. So the aliasing that appears in the first stage then also appears propagated in the second and following stages. So it propagates through the cascade. This reduces compression performance or the reconstructed quality. Right? So this can be seen here in this plot. So here I have an example, one-dimension example. So example, for instance, for the rows. Here I have 3 stages with non-perfect filters. And after each downsampling, we will get aliasing because of non-perfect filters. And then I'm looking at the frequency resolution or the frequency response at this point here. Right, so this is the frequency response at this point after 3 stages, and we should get a passband which is 1/8 of Nyquist, which we can see here. So this is ideal, the dashed line. This is the passband, so this is fine. So that looks okay. Then we have a fairly wide transition band, which was to be expected. But now we are also getting those peaks here, right, which is not so good. Right, so we get a very poor attenuation, and this is a combination of the magnitude response of the 2-band filter and also from aliasing. So that reduces our compression, because that means that frequencies that appear here also appear in the higher subbands. We still have a linear phase, which is important because that means we get the same delay for all the frequencies. And for that we have to know that the delay from filtering comes from the slope of the phase. So the slope of this phase function gives us the delay through the filter at different frequencies. So at each frequency we have the same slope, and that means we have the same delay, and this is important for keeping edges together again. Yeah, so here it's important for images because edges have components at all frequencies, Edges are basically a step function, and a step function has a very broad frequency response. And if these would be delayed differently, edges would appear fuzzy. So we don't want that. Yeah, so linear phase means we have a phase as a linear function of frequency f, as we can see here. Here we have the frequency f going from 0 to 1, and here we have the phase, and we can see it's a linear function. And the slope represents the resulting delay at all those frequencies. Yeah, so that's it for this set of slides. Thank you for your attention, and see you next time.